Can I kick off by asking each of the panelists just to very briefly introduce themselves and their organization? Carmen.
Hi, yes. Hi, everyone. I'm Carmen. I'm co-founder and CEO of New Quantum. We're a quantum networking company based in Cambridge, and we're building quantum interconnects to scale quantum computers.
Good.
Just in case anyone missed your earlier presentation.
Winfried Hensinger, I'm a professor of quantum technologies at the University of Sussex, with exactly 50% of me, and the other 50% is co-founder, chief scientist, and chairman of quantum computing company Universal Quantum.
Robert.
Hi there, I'm Robert Axmann. I'm working for the German Aerospace Agency, heading the German Quantum Computing Initiative.
Hi, everyone. I'm Dorita Aronov. I'm a professor for computer science at the Hebrew University of Jerusalem. And I'm also the CSO of Kedma Quantum Computing, doing error mitigation.
Yong.
Thanks. Hi, I'm Yang Chen. I'm a physics and electrical engineering professor and also director of Purdue Quantum Science Engineering Institute at Purdue University in the US. But I also have research operations in Denmark and Japan, so I'm a little bit superposition.
So I wanted to kick off, because sometimes when you listen to the hype around this, you can kind of assume that the development of quantum is going to just take care of itself. But Yong, I wanted to lead off with yourself. Quantum computing promises all of these unique computing capabilities. Why is pinning down real-world use cases proving so hard?
Thank you for the good question. In my observation, so I think there's both hardware challenges and what I call software challenges, and you alluded to some of that in your talk. It's challenging to make bigger quantum computer, right? The quantum computer we have today is a baby version that's relatively small and also very noisy, and it's just very challenging to make one. It also require a lot of the extreme physical conditions, cryogenic, all that. So that's one aspect. But a lot of challenges on the software side, again, very broadly speaking. I think our thinking may still be too classical. We don't have enough, they're experts here, to actually have the right algorithm to really utilize the true capability of the quantum computing. I mean, we have some small number of examples, but we don't really have a general purpose kind of algorithm. So I'll just leave that. I think that's a great topic.
Now, Winfried, I wanted, this follows on from your talk to my mind. You left us in no doubt that you're committed to this fault-tolerant quantum computing. Why is it that you prioritize that goal so much?
I think maybe some of you guys maybe seen Jay Gambetta's talk on IBM and this quest of build 100 times 100 machine. I don't know how many engineers are in your audience, but you have to, in a way, go towards your goal by setting milestones, by setting a path that is appropriate for the destination you do. And a million qubit machine requires very different technologies than a 100 qubit machine. A 100 qubit machine has all different challenges, and to demonstrate quantum advantage at NISQ is its own challenge, and actually very hard, as you noted. Now, we're not trying to solve everything, and we can't, and we don't have that capacity. But we are there purely and only to go to these large-scale machines, but that means we have to very critically question the technologies we apply in order to get to that point. Now, it's very hard to imagine using laser beams at that scale of millions of laser beams to do so, but it's very easy to imagine to build a 100-qubit quantum computer with laser beams. So if you want to do that, if you wanted to beat somebody to have built a slightly better 100-qubit quantum computer, lasers would probably be a better choice. But if you're really serious about scaling up, you're going to have to do some of the hard groundwork right now, and you have to set the milestones and deliverables in such a way to go to this large scale. I don't believe it's the right thing to just say, look, we're going to build a 50-qubit quantum computer right now, and hopefully, if that's successful, some funder will give us plenty of more money, and then we're going to change entirely course and build something different. I think it's right, and it's good to focus on one thing, and I believe personally, and that's my personal belief and my personal enthusiasm, we need to develop the technology to really work at scale, and this is why we must choose different engineering solutions than other companies, other stakeholders that might want to work at NISQ.
Now, I want to go next to someone who I'm thinking is going to have a different perspective into this. Dora, do you see that there is a route to commercial quantum advantage with NISQ devices?
So let me say, I actually agree totally with what you said, in parallel to the fact that we do we do want to get to we do want to pick some fruits along the way from quantum computation before we get to the I don't know if end is the right thing to call it, because it's a long path even when we reach fault tolerance. I do very enthusiastically believe that we will see in NISC devices quantum advantage already. And I think also following what Jay Gambetta was talking about earlier, I think that it's pretty reasonable to pretty viable belief that we will reach something of the order of 1,000 qubits, or even more, maybe a few thousands of qubits, logical qubits, very in the near future. Within, I'm quoted. I'm photographed, but I'm going to say it. Within the next few years of 2, maybe 3 years, maybe 4, just for the photograph. But I think this is a reasonable goal. And I think we can see this very soon. And I think that 1,000 logical qubits with error mitigation in NISC devices is the same as the number of physical qubits. This will happen before we reach 1,000 logical qubits on fault tolerance. So I think this is a good stepping stone to go to.
Mm-hmm. Now, Carmen, I wanted to come to yourself. The title of this panel is about getting all hands on deck to make this happen. Is that the right way we should be thinking about this? Do we need to get all hands on deck?
Yeah, definitely. I think, fault-tolerant quantum computing is not only the kind of moonshot of our generation, but we're building literally a completely new industry, right? So it's not just about qubit companies anymore. A few years ago, the focus was qubit companies, but now we're seeing, all areas of the industry, of the stack and the industry come through. We had a few years where there are a lot of, for example, control companies and attention on that, error correction. Now people start to realize how important the interconnect layer is, that co-physical layer with the qubits. This year we've seen a lot of talk about integration with data centers, right, and integration with classical computing, infrastructure, right, cryogenics. PsiQuantum and the UK government are now developing, have a strong effort in developing cryogenics. And lastly, but very, very important, end users. We need a lot of pull from end users. We need end users that are educated in quantum, that have quantum teams, because no one understands their problems like they do. And so that needs to be built out as well. So yes, I think that's what all hands on deck means for fault tolerance.
I wanted to come to Robert. Now, for those that maybe haven't followed, DLR have just put a lot of money into backing a series of quantum computing projects. And you've cast the net pretty wide, Robert. Why has that been the right thing to do?
Yeah, that's true. So we got out of the 2 billion of the German government, 740 million. And what we first did is we did a market estimation. So what's going on the market? What are the startups offering? And if I would go and ask Winfried, what's the best technology? I think the answer would be something like ions. But if I ask someone else, it might be something like photonics or NV centers. So we discussed a lot with our boards, with our internal science boards and industrial boards. And finally, we found that for the first round of activity, it's important to be technology open. So all the different platforms do have different coherence time, do have different gate fidelities, do have different operating temperatures. So some weeks ago, we got our first system delivered from XEQ, an NV Center room temperature system. And I'm really happy that we are getting additional systems with other technology bases in the next months also. And up to now, we procure really open based on the technology, and we will see how those systems perform. And the key is now the performance within the next years, let me say up until 26, 27. And after that, I think there will be something like a process where we do have to focus, at least concerning the hardware platforms, on a subset of all those platforms now covered.
So I want to move on to scaling up in general, and scaling up looks like it's a hard challenge. And Winfried, let me overly characterize like this. Physicists, we're used to the caricature of a physicist. It's tinkering with the immediate problem at hand. Now, you've really championed this approach of thinking through a long-term approach. And you already, I think you already began in your presentation to sketch out why you think that's necessary. But I guess is it realistic to plan that far ahead?
I think I've learned that actually I'm going to out myself. As in starting my career as a physicist, doing experiments in my lab, I didn't always plan ahead that far. In fact, as a physicist, we all know when physicists do the electronics, it's an utter disaster. Cables coming out everywhere. And this made me realize this is very well if you want to write a Nature paper, this is your thing, if you just want to have academic progress. But it's not the right thing if you want usable technology that is being utilized by users to solve disruptive industry problems. For that, you need engineers. Now, but the engineers don't understand quantum physics. And so you can't just bang a bunch of engineers on the problem, because that's equally not going to work. So you're going to really have to plan this out. You're going to have to find the programmers with the right programmers, and you have to give them the right milestones, and you have to have a flat structure where you bring the engineers next to the physicists. And that's exactly what we do in our company. We have a flat structure where a leading quantum engineer or quantum physicist sits next to a CMOS engineer whom we got from some foundry, who really helps us to plan the CMOS and also tells us, like, don't you dare to want that. A physicist will say, I want this specification to be the best. And this is entirely inappropriate for an engineer. An engineer will ask me, you need to tell me the specification, I'm going to tell you the time frame and the cost for that. And so this type of working I've learned with working really leading engineers from across the world, that was very novel for me as a physicist. But only with these type of interactions, really bringing people, software people, engineers from all different domains, and a bunch of physicists as well, only that will actually deliver a useful quantum computer. And so I'm really, and I can see the difference between my research group and the company. So what huge difference that makes.
Carmen, I wanted to come to you on the point of photonics. You know, photonics, you scrape at any of the qubit platform approaches, and some, they all end up wanting a bit of photonics somewhere, it seems. Can you talk to us a bit more about what are the challenges of getting photonics to play nicely with all of these different platforms?
Yeah, absolutely. No, so you're totally right. So some technologies already use photonics for lasers, for example. So ions and atoms use photonics, but actually all technologies will use photonics, and that's simply because of scaling challenges. So there is no qubit technology that can get to 1 million qubits in a single core. That we don't know how to do that. In fact, you know, if we talk about numbers, if we think that perhaps in monolithic scaling we can get to around 1,000 qubits, a few thousand qubits, then that means you need to interconnect 1,000 cores to get to 1 million qubits. That's a huge technical challenge. The largest quantum network that exists today is a 3-node network. So you know, there's a lot of big challenges to do with the networking and interconnect layer. And there's a specific challenge around the kind of matter-light interface. That's really where a lot of the bottleneck is, getting to qubits to send their information as photons rather than stay within the matter qubit. So that's really the greatest bottleneck, and that bottleneck is a much harder challenge for superconducting and spin qubits, for example, than it is for optically active qubits like atoms and ions.
Yeah, Dorrit, we've become used in the field to talking about error suppression. We've had Jay already talking today about error mitigation. Can you tell us a bit more about what the opportunity of error mitigation is going to be, but also what are the challenges of getting it to then work with the algorithms we want to put on top?
Okay, yeah, so this is actually related to what you're talking about the gradual transition versus the getting far ahead in time. I think the challenges, there are many challenges for making error mitigation work with algorithms. And one of them is, I guess the question is not just about how to make error mitigation work, per se, but how to actually adapt quantum algorithms to that. Is that right? Okay. The problem is, so me being a computer scientist, a theoretical computer scientist, I always thought of quantum algorithms as algorithms, not quantum algorithms, as something that you write pseudocode and that's it. The rest is just a technical little thing that you implement and that's it. But in fact, implementing an algorithm, given the idea of the algorithm, is a full story on its own, especially adapting to particular machines and particular architectures, etc. And putting on top of that the extreme requirements coming from error mitigation, and in terms of geometry, in terms of pushing qubits around, in terms of choosing the right qubits, etc. This is really, really challenging. So this is, I think, a whole new field of research of how to actually combine the two things. So this is a big challenge in my mind.
Now, Yong, I wanted to come to you about the question of the different qubit platforms, modalities we already have. Do we really need more?
My personal opinion is I think we should be open-minded. I recognize, of course, their current front-runners, trapped ions or superconducting qubits. But if history is some guide, I look at the history of classical computing. If you go back to the 40s, for example, when the first generation transistor emerged, the first generation classical computers, those transistors based on germanium semiconductor bipolar transistor. And that kind of went on for almost several decades until kind of silicon and MOSFET kind of took over. So I would not be surprised if later some kind of evolution of materials or entities happen in quantum computing. So I think we should have some humility and also be open-minded. But of course, have some focus. I mean, we learn tremendously with the system we're working with right now. But I think we might still be looking for the silicon for quantum computing, which we don't know today. It's possible.
So I want to come on and try and talk about the challenge of error correction a bit. And and I introduced that a bit in my talk. But Winfried, you've done significant work in your architecture, which does offer enhanced connectivity. You've also done a lot of work on the surface code. How do you feel about this question of different error-correcting codes?
So there's a lot to say about that. So in 2017, we published a paper where we calculated what type of quantum computer it would take to break RSA encryption. And the answer at the time, with conservative specifications, it was a machine 100 meters times 100 meters. So it was a football field. We got a headline in Nature, physicists propose football pitch-sized quantum computer. So since then, we've done a lot of theory, and some of that theory was, as you say, about the right codes. And trapped ions have this really, really enhanced connectivity. So what do I mean by enhanced connectivity? One ion can speak to 1,000 or 10,000 other ions. So not just nearest neighbor, but 10,000 other ions. What it means is that we need codes that can actually effectively make use of this enhanced connectivity. The surface code traditionally was made for solid-state architectures for superconducting qubits, because that's what people believe then. That is the type of architecture that would be successful. So many theorists just worked on that. And the surface code only makes use of this nearest neighbor connectivity. So just to take this, show you like where this already led us. So the machine to break RSA encryption, which in 2017 we felt was 100 meters times 100 meters, is now 2.5 meters times 2.5 meters, in part because of using different codes. So what we need is theorists to really make use of this tremendous opportunity in trapped ion quantum computing, and actually to really, really work on codes. And there's actually very little work done, and we work with a lot of theorists on that topic. And so this is really, really important. Equally important as developing the hardware is to develop the codes that can make maximum use of this enhanced connectivity. On what that means in practice. It means in practice that we need a lot less trapped ions, and maybe for the people who actually run applications or want to run applications of a quantum computer in this room, it means you will be able to run that disruptive application for your industry sector maybe 5 years earlier, because instead of 10 million qubits or even a larger number, you might just need 50,000 qubits. So this is a tremendous opportunity for trapped ion systems, also for neutral atom systems, and I think we should really capitalize that. And this is actually really, really good news for anybody who wants to use quantum computers for disruptive applications.
Jorn, I think many people in the audience will have heard this very interesting Quantinuum announcement on the non-abelian anions. And maybe you could take us through, why is there this interest in topological error correction?
Thank you. First of all, I should admit that I don't really work much on error correction myself, but I work on topological quantum materials. So topology is dear to my heart. So from a very general point of view, of course, the concept, if you can encode information in the topology, whether it's the difference between a closed and open ring, the knot of of the rings, if that can be utilized, that's very powerful. Whether it's you can implement some topological error correction code or topological scheme on the kind of quote broadly software kind of level to make the error threshold more friendly, that would be very, very powerful, of course. Or more broadly, right? If you can even building hardwares or qubits that can use topological states or quasi-particles like non-abelian anions that are more intrinsically resistant to noise and error, that will be very powerful. With the challenge that the real systems, the practical quantum computer, may not be exactly described by the Hamiltonian of topological. There may be other factors that one have to kind of deal with. But overall, it allows us to maybe do useful things with a more noisy systems and environment. So I think that's the big motivation behind it. Thank you.
So Carmen, I wanted to come to you on this as well. These photonic interconnects you're talking about, they're going to help with error correction?
Absolutely, they're really going to help. So as we've heard, error correcting codes are designed to be used on certain architectures with a certain connectivity. And if you think about monolithic computing, then you're restricted to the connectivity of your qubit. So for ions, that's really good. It's also all connectivity. For superconducting, it's a 2D lattice. So you're restricted to the surface code. But now think about what happens when you're interconnecting different nodes together photonically. You have suddenly the ability to create these long-range links that are flexible, that are potentially dynamic, and that allows you to create a kind of meta entanglement topology, which is suited to perhaps a more powerful error correcting code. And again, reduce those ratios. So absolutely, the interconnect photonic layer will help.
I wanted to move on and in the last minutes remaining, just talk a little bit about the role of national quantum strategies, clusters, ecosystems.
David, can I make one comment before that?
Yeah, please.
Just saying, I think that overall about both the quantum error correction codes as well as quantum algorithms, which we didn't talk a lot about, I think there is not enough emphasis on the role of new ideas. Yeah. From the point of view of how we plan ahead. It seems like we're thinking all the time in our minds that what we have now is what we'll have in a few years in terms of ideas, because it's so hard, so bloody hard to implement those ideas. But if you look at the history of quantum computation, basically it's the ideas, it's the breakthroughs that completely shifted the whole field, starting from Shor's algorithm and Bernstein-Vazirani and quantum error correction, et cetera. And one single such idea can completely change the whole ecosystem. And I think we should not only take that into account in terms of our agility and our flexibility, but also we should plan and invest more in creating the ecosystem that will generate such new ideas.
Yeah, that's a good point. I wanted to. I was very. I wanted to try and get Robert on the spot on a particular ecosystem question, because everyone wants to create an ecosystem and create clusters to build their economic career, and everyone wants to found the quantum Silicon Valley. And Germany's already benefiting from 5 federal state level initiatives. But there are difficult trade-offs. How many quantum clusters does Germany need? How many does the EU need? How many does wider Europe need?
It's a difficult question. So the positive side of the coin is that you are triggering attention with politics. So and the money we are working on, it's taxpayers' money at the moment. And on the other hand, one must see that most of the local clusters, for example, like Munich Quantum Valley, or the Hanover cluster, for example, they concentrate on universities and non-university research organizations, and they do have some millions, not billions. So I think it's very positive that we have that many clusters, and I do see the same in the UK, for example. We do have the hubs, the NQCC, and maybe more initiatives. So I think that's not bad, but of course what we are doing in Germany, we are fostering the exchange between all the local initiatives and the federal initiatives. And we do have 2 of the federal initiatives, so the more academic initiative by the Ministry of Research, focusing on university and demonstration of quantum computing technologies, and our initiative focusing 80% of the money onto industry, startups.
Just in the minute remaining to us, and for the geographic balance, I wanted to come to Yong on this question of ecosystems. Obviously, the US benefits from tremendous breadth of very strong universities, and it's got some great large tech players, of course. Got some great startups. Where do you, recognizing those strengths in the US ecosystem, where do you think the US needs to do more?
Oh, thank you. If I may, again, borrow a quantum analog, I think to have the best, most powerful quantum ecosystem, it needs to have strong coupling and construct interference, coherence among different players, including university, of course, the great university here as well, and strong companies, private sector. It also needs to be open quantum system, coupled in the outside environment in the right way. So more specifically, I think, in no particular order, I think US in general can do better to attract more do better in workforce development, including attract more students in even earlier stage to enter STEM field. I think that can do better, including more women also. And another area is to find the right balance between kind of protectionism. I mean, there's company and university IP, but also international collaboration, attracting the best talent from all the world, maintaining open science, also balance with, of course, the protection of the national economic security, all that. And also to have a stable, continuous, strong support to science. That is kind of not swing back and forth. I think these are things that can be strengthened.
Now, we are over time, so please join me in thanking our panelists.
Thank you.